Hi, my name is Chris Loker. I'm an applications manager for signal chain products at Linear Technology. Let's talk about how you use differential op-amps to work with differential analog signals. Differential signals come into play when working with high-performance A to D converters, which often require driving a fully differential signal into the analog inputs. Differential signals are also handy when you need to transport an analog signal over some distance, such as from one board to another. If we move signals differentially over a well-balanced differential cable, much of the environmental noise pickup will be common to both wires. We can later extract the difference between these two noisy wires. A differential op-amp looks in many ways just like a regular op-amp, except that it has two outputs instead of one. It too has high gain from the differential input to the outputs, so that if we wrap feedback around it, the difference between the two input terminals forms a virtual ground. You usually apply feedback using 4 resistors, as shown here. The gain is set by the ratio of the feedback resistors to the input resistors. And notice the equation. The difference between the two outputs is determined by the difference between the two inputs, not by the actual voltage on either of the inputs separately. We often use the circuit as follows. We ground one of the inputs and apply our regular single-ended signal to the other input. Then we see that the op-amp creates a differential voltage at the output proportional to the single-ended input voltage. That is a single-ended to differential conversion. You may notice another pin in this circuit that I haven't yet discussed. It's labeled VOCM, which stands for Output Common Mode Voltage. To see what that does, let's take a look inside. Inside a differential op-amp, there are actually 2 op-amps. Besides the one that we usually show, there is another op-amp connected like this. 2 internal resistors measure the instantaneous average, or common mode, of the 2 outputs, and feed that into one of the terminals of this error amplifier. The other terminal is driven by the external VOCM pin. The output of this extra op-amp connects into the main op-amp in such a way that it pulls both outputs up or down in the same direction. This loop forms negative feedback, causing the common mode of the 2 outputs to be identical to whatever voltage you set on the VOCM pin. Let's look at an example where this is important. This schematic shows a high-speed ADC, the LTC2185 16-bit low-power 125 megasample per second ADC. This ADC is powered from a 1.8 volt supply and requires that the input signals are differential and centered on a common mode voltage of just 0.9 volt. On the other end is the LTC5585, which is an RF demodulator, which frequency translates an RF signal to a DC-coupled baseband output. Because of the way that that component is constructed, its DC level is higher, at about 3 volts. In between is the LTC6409 differential op-amp. This op-amp has the kind of low noise, low distortion, and high speed needed to work with the most advanced radio communication schemes. And importantly, it allows you to couple a 0.9 volt bias voltage from the ADC into the VOCM pin of the LTC6409, which biases the common mode level of the outputs at 0.9 volt, right where the ADC needs them. You might think that differential op-amps are mainly for high-speed communication circuits. Nothing could be further from the truth. Linear Technology now has a family of SAR ADCs meant to digitize relatively low-speed signals at excellent DC accuracy, and with a signal-to-noise ratio of more than 100 dB. To achieve that level of performance, we need to drive a differential signal into the ADC. The LTC6362 has been specifically designed for these types of applications, as shown by its 200 microvolt offset voltage, rail-to-rail output, and low power supply current. There are many more things that you can do with differential op-amps. You can build active feedback filters, now by connecting a set of resistors and capacitors differentially around the op-amp, just as you can with regular op-amps. As always, the tolerance of the passive components is an important consideration when building such filters. Linear Technology also offers integrated filter products, such as this LTC6601, which combines a differential op-amp with a set of on-chip, laser-trimmed, tightly matched resistors and capacitors. In conclusion, differential op-amps are important building blocks in modern analog and mixed-signal circuits. Linear Technology has a large and growing portfolio of differential op-amps covering both low-power precision as well as very high-speed applications. Please visit linear.com for more information. Thank you for watching.